Now, consider that we are not interested in a single occurrence or a single failure or a single happening in a Poisson process. In place of that, we are considering, so consider a Poisson process let us denote x t with rate lambda and let x r denote the time, well in place of x we will use notation say T r because x is being used here. Let T r denote the time of rth occurrence. So, in place of the first occurrence we are looking at a certain number of occurrences, as we had discussed yesterday also, like in the negative binomial distribution, that a certain major event may occur as a consequence of certain smaller events. For example, if 1000 smaller intensity earthquakes occur, then it may make the earth to crumble and a major earthquake may occur. A sequence of certain mishaps may close down the plant itself. A sequence of, so any smaller kind of events may lead to a major disaster. So, we may be interested in the waiting time for that, of course, considering the events to occur in a Poisson process. For example, a certain number of occurrences have occurred, say a certain number of people purchase certain tickets, then we may have to close down the window because the seats are full. So, what is the distribution of T r? Once again we can consider probability of T r greater than T. So, starting from a time 0, consider time small t. If we say that rth occurrence has not taken place till this time, suppose this is the rth occurrence, that means in the interval 0 to t less than or equal to r minus 1 occurrences will be there. So, this event is equivalent to probability of x t less than or equal to r minus 1. Of course, here t is positive, it is equal to 1 for t less than or equal to 0. Now, x t is having a Poisson distribution with parameter lambda t. So, this is equal to e to the power minus lambda t to the power j by j factorial summation j is equal to 0 to r minus 1. This is for t greater than 0 and it is 1 for t less than or equal to 0. Consequently, we can write down the cumulative distribution function of T r as f of T r at the point t, that is 1 minus probability of T r greater than t, and this is equal to 0 for t less than or equal to 0, it is 1 minus summation j is equal to 0 to r minus 1 e to the power minus lambda t to the power j by j factorial for t greater than 0. So, you can observe here it is a time variable and this is an absolutely continuous function. So, the probability density function can be obtained by differentiation of this . Now, for t less than or equal to 0 it is 0 and in this particular portion we are having sum of a series. So, we have to do term by term differentiation. So, this is equal to 0 for t less than or equal to 0 and in this portion now this is d by dt of e to the power minus lambda t plus lambda t into e to the power minus lambda t plus lambda t square e to the power minus lambda t by 2 factorial and so on plus e to the power minus lambda t to the power r minus 1 by r minus 1 factorial for t greater than 0. So, here you observe that when we differentiate, here one term is there, but thereafter each term is a product of two terms involving t. So, when we differentiate, we have to do by applying the formula of derivative of a product. So, if we expand the terms, the derivative of the first term will give us minus lambda e to the power minus lambda t, and there is a minus sign here. Consequently, we will get it as lambda e to the power minus lambda t. If we look at the second term and we look at the derivative of this, we will get lambda multiplied by e to the power minus lambda t, and there is a minus sign here. So, we will get here minus lambda e to the power minus lambda t, and observe that this can cancel out. The next term will be the derivative of this. So, that will give minus lambda, and minus is there. So, it becomes plus lambda square t e to the power minus lambda t. Now, look at the third term and derivative of this. So, if we look at the derivative of this one, here t square is coming. So, 2 t and this 2 will cancel out, and there will be a minus sign. So, we will get with a, because there was a minus sign outside, it becomes minus lambda square t to the power minus lambda t. So, you can easily observe that this is a telescopic sum. The final term will be plus, which will be contributed by this term, that will become lambda to the power r t to the power r minus 1 by r minus 1 factorial e to the power minus lambda t. So, this will be the left out term. So, we are getting the probability density function of T r as lambda to the power r t to the power r minus 1 e to the power minus lambda t by gamma r for t greater than 0. Here lambda is a positive parameter. In the derivation, we have considered r to be a integer because it is occurrence, but after writing down this, you can see that it is valid for r greater than 0, any positive real number. So, this is known as a gamma distribution or Erlang's distribution. So, this distribution arises as the distribution of the waiting time for the rth occurrence in a Poisson process in place of the first occurrence. If you put r is equal to 1, you will get the exponential distribution, because this term will vanish, you will get lambda e to the power minus lambda t. So, this is a generalization of the exponential distribution, but it has much more applicability, because we are looking at a higher order of occurrences in a Poisson process. Apart from the regular applications, one can see the characteristics of this distribution. If we consider a kth order non-central moment, that is mu k prime. So, mu k prime is equal to integral from 0 to infinity t to the power k lambda to the power r t to the power r minus 1 by gamma r e to the power minus lambda t dt. So, obviously, this is a gamma function. You can write it as lambda to the power r by gamma r t to the power k plus r minus 1 e to the power minus lambda t dt. So, it is lambda to the power r by gamma k plus r divided by lambda to the power k plus r. This is equal to, that is mu k prime is equal to gamma k plus r Of course, this is valid for any k greater than 0, but we will be more concerned with the positive integral moments. So, mu 1 prime is equal to gamma r plus 1 by gamma r 1 by lambda, that is r by lambda. So, if the waiting time for the first occurrence was average waiting time for the first occurrence was 1 by lambda, then for the rth occurrence it will be r by lambda. So, this is again because of the memoryless property of the exponential distribution, because after first occurrence we can again consider it as the starting of the process observing from time 0. So, again for the second occurrence waiting time will be 1 by lambda and so on. If we consider mu 2 prime, then this becomes r into r plus 1 by lambda square, and therefore, mu 2, that is the variance of this distribution, is equal to r into r plus 1 by lambda square minus r square by lambda square, that is r by lambda square, which is again you can see in the exponential distribution the variance was 1 by lambda square, and if we are looking at the variance of the rth occurrence, then it becomes r by lambda square. Let us look at one application of this. The CPU time requirement T for jobs has a gamma distribution with mean 40 and standard deviation 20. This measure is in seconds. Any job taking less than 20 seconds is a short job. What is the probability that of 5 randomly selected jobs, at least 2 are short jobs? So, in order to answer this question, let us consider the setup. Here mean is given to be 40. So, that is r by lambda is 40 and standard deviation. So, here variance is r by lambda square. So, r by lambda square is 400. So, this is a 2 parameter distribution and we have now 2 equations. So, we can have r by lambda is equal to 40, r by lambda square is equal to 400. So, if we solve this, we get r is equal to 4 and so lambda is equal to 1 by 10. So, that is right. What is the probability of a short job? That means, t is less than 20. So, we need to consider the density function of t here. F t is equal to e to the power minus lambda t. So, that is t by 100, t to the power r minus 1, that is 3, then lambda to the power r, that is 1 by 10 to the power 4, and gamma r. This is for t greater than 0. So, we need to calculate 0 to 20 the integral of this density 1 by gamma 4, 10 to the power 4, e to the power minus t by 10 t cube dt. This is the probability of a randomly selected job to be a short job. So, if we want to evaluate this, we can consider, since exponential function is involved, the integral will be at one end something value 1 and at another point some value will be there. So, it is convenient if we consider this as 1 minus 20 to infinity 1 by 6 into 10 to the power 4 e to the power minus t by 10 t cube dt. So, from the integrals integrand we can observe that it is convenient if we put t by 10 is equal to y, that is 1 by 10 dt is equal to dy. So, this becomes equal to 1 minus, this will be 2 to infinity 1 by 6 e to the power minus y cube dy. So, this is not a complete gamma function, this is an incomplete gamma function, because the integral is from 2 to infinity. So, we can do integration by parts, and after doing certain simplification, this one will turn out to be 1 minus 19 by 3 e to the power minus 2, which is approximately 0.1429. So, probability of a randomly selected job being a short job is only 0.1429. That means, in the gamma distribution, if the mean is 40 and the standard deviation is 20, the probability of job being over in mu minus sigma is actually much smaller. Now, we can consider the random variable, say z is the number of short jobs out of 5. Then z is following binomial distribution with n is equal to 5 and p is equal to 0.1429. This is p, this is n. We are saying what is the probability that at least 2 jobs are short jobs. That means, probability of z greater than or equal to 2. This we can consider as probability z is equal to 0 and z is equal to 1, you subtract from 1, that is the complementary event. So, this is equal to 0.1 minus 0.1429 to the power 5 minus 5 c 1, 1 minus 0.1429 to the power 4 into 0.1429. So, this can be evaluated and it is approximately 0.1519. So, the probability that at least 2 out of the 5 jobs are short jobs is quite small. This is because the probability of a single job itself being short job is much smaller. So, we may look at the moment generating function etcetera of this distribution. So, moment generating function of the gamma distribution, expectation of e to the power u t r, that is equal to integral e to the power u t lambda to the power r by gamma r e to the power minus lambda t t to the power r minus 1 dt 0 to infinity. So, here if you see, this term can be combined with this. So, it becomes directly a gamma function. So, this is equal to lambda to the power r by gamma r e to the power minus t lambda minus u t to the power r minus 1 0 to infinity. So, this is just the gamma function lambda by lambda minus u to the power r and gamma r will be cancelling out. So, this is valid for u less than lambda. You can see the similarity from the moment generating function of the exponential distribution, where r was 1. So, it was lambda by lambda minus u. So, We will show some relationship between the gamma distribution and the exponential distribution later on. The moments of the gamma distribution, as we have seen, can all be calculated from the general expression for mu k prime. So, mu 3 prime, mu 4 prime can be calculated, and then mu 3 and mu 4 can also be calculated. You can see that it will be actually positive. So, all the gamma distributions will be in fact positively skewed. The reason is that if you look at the density function, it is lambda to the power r t to the power r minus 1 e to the power minus lambda t divided by of course gamma r. So, in the beginning, if you consider at t is equal to 0 apart from r is equal to 1, this value is going to be 0, and if you are considering then t becoming larger, then in the beginning, since it is t to the power r minus 1, it may increase little bit, but thereafter this term will dominate, and therefore, the densities will always be positively skewed for various gamma distributions. Of course, it will depend upon what is the value of r and what is the value of lambda for different shapes, but whatever be the shapes, they will be positively skewed. The peak will of course depend upon the value of the r and lambda. If we are considering the exponential distribution or the gamma distribution as the life of certain components, then another interesting distribution in the same direction is the so called Weibull distribution. The general form of a probability density function of a Weibull distribution is given by alpha beta x to the power beta minus 1 e to the power minus alpha x to the power beta, where x is always positive and alpha and beta are positive parameters. So, quite naturally one can see the form of the CDF here, because if you integrate from since x is positive valued random variable, the integral will be from 0 to x f t dt for x positive, and it is 0 of course for x less than or equal to 0. So, if you consider this integrand, it looks like a derivative of e to the power minus alpha x to the power beta, and therefore, when we calculate the CDF, this will be simply equal to 1 minus e to the power minus alpha x to the power beta for x positive, and it is 0 for x less than or equal to 0. If we put beta is equal to 1, then this term vanishes, this term becomes e to the power minus alpha x. So, you get alpha e to the power minus alpha x. So, that becomes exactly the density of an exponential distribution. So, this Weibull distribution is actually a generalization or extension of the exponential distribution. So, we will see that what is the significance of making power x to the power beta here, because in the exponential we had alpha e to the power minus alpha x. So, x has been replaced by x to the power beta. So, first is that we can look at its moment structure. So, obviously, you can make use of the gamma functions. If I consider expectation of x to the power k, it is alpha beta x to the power beta plus k minus 1. So, quite obviously, you can understand here that if we put x to the power beta is equal to y, that is beta x to the power beta minus 1 is equal to dx is equal to dy, then this becomes integral from 0 to infinity alpha and x to the power beta minus 1 term is combined here. So, you have x to the power k, that is y to the power k by beta e to the power minus alpha y dy. So, this is simply a gamma function, and the expression for this turns out to be alpha gamma k by beta plus 1 divided by alpha to the power k by beta plus 1. That means, gamma k by, or you can write it as k plus beta by beta divided by alpha to the power k by beta. So, in particular, if I am looking at the mean, so mu 1 prime is equal to expectation of x, that is equal to alpha 1 by beta plus 1 gamma of this divided by alpha to the power 1 by beta plus 1, that is equal to alpha to the power minus 1 by beta gamma of beta plus 1 by beta, and mu 2 prime will become alpha to the power minus 2 by beta gamma of beta plus 2 by beta, and therefore, the variance of the Weibull distribution will be alpha to the power minus 2 by beta gamma beta plus 2 by beta minus gamma beta plus 1 by beta whole square, which looks slightly complicated, but nevertheless, the functions of the gamma functions can be easily calculated using tables of the gamma distribution, or the from calculators or computers nowadays. This can be easily. However, this distribution has more importance in the reliability analysis of certain mechanical or electronic systems. So, let us define what do you mean by the reliability of a system. So, if T denotes the survival time or the life of a system, so we can consider probability of T greater than T. This means the system has been functioning till time T, or it has not failed till time T, or the system is working at time T. The probability of system working at time T is called the reliability of the system at time T. Reliability of the system at time T. So, using this we can define another quantity, and of course, you can easily see that this is equal to 1 minus the CDF at the point T. We also define what is known as instantaneous failure rate of system at time T. So, let us consider the interpretation of this. The system is functioning at time T, and immediately after the time T it fails, that means in an interval from T to T plus h. So, if we are considering the rate, we consider it divided by h and take limit as h tends to 0. Let us give some notation, say h of t, we also call it hazard rate at time t. So, this we define for any random variable which is denoting the life of a system. So, we call failure rate at time t or hazard rate at time t. That means, given that the system is functioning at time t, what is the probability that it will fail immediately after that, and therefore, if we want to calculate the rate, then we divide by the length of the interval and take the limit as this. So, let us evaluate this. Now, if we consider this as event A and this as event B, then this is probability of A intersection B divided by probability of B. Now, once again you can see that A is a subset of B. So, this becomes probability of T less than capital T less than or equal to t plus h divided by probability t greater than t h, limit as h tends to 0. So, this term if you see, it is nothing but the density function of the variable t, because we are taking limit as h tends to 0. See, you can expand it like this, the numerator becomes f of t plus h minus f of t by h, and this is r t. So, this term is nothing but the f t by r t, or you can consider it as f t divided by 1 minus f t. So, the hazard rate of a lifetime distribution can be denoted by the density divided by the reliability, or the density divided by 1 minus the cumulative distribution function of the random variable. So, we are calling it as h t. We can notice another relationship here. This is minus d by dt log of 1 minus f t. So, this looks like a first order differential equation. We can integrate it out and we will get log of 1 minus f t as equal to and therefore, plus of course, a constant of integration. So, 1 minus f t becomes some k times e to the power minus integral h t dt. This shows that given the distribution, one can calculate the hazard rate, given the hazard rate function, one can determine the CDF and hence the probability density function of the random variable. We will look at these quantities, that is the reliability, the hazard rate in context of the Weibull distribution, the exponential distribution, and try to see what does it signify. So, in the next lecture we will be covering these issues. Thank you.